Hello, I'm Aya El Sayed presenting the feedback dynamics of brain-computer interfaces in a distributed processing environment. It's a distributed paradigm for human brain-computer interfaces that can easily incorporate machine learning directly stimulus feedback to the subject. We used OpenPCI hardware and software to capture real-time EEG forms from a subject on a host client computer and stream them to another server computer, which could perform complex analysis on the waveforms to send commands back to the OpenPCI interface directing alternations to the stimulus. We will also present the test results quantifying the closed-loop system latency under various conditions. This is a vital step for any feedback controlled loop system, especially the one that actually contains the brain, since any access latency can destabilize the system. BCI allows us to control a device by changing our brain activity, relying on the measured brain activity. It's been used to assist, enhance, or even understand the cognitive or sensory motor functions. Another important concept is neurofeedback. It's a kind of biofeedback where assessmenting of occurring brain state reported by EEG, EMG, fMRI, or any other brain imaging tool, then the reported brain activity is mapped to a feedback signal for controlling various devices through computer interfaces. There are different types of neurofeedback. Open loop brain state independent brain stimulation, where the PC controls the stimulus without having any idea about the brain state. Secondly, open loop brain state dependent brain stimulation, where the current brain state is being monitored and analyzed to adjust and trigger the brain stimulation accordingly. Here, the output doesn't affect the future brain state. Lastly, closed loop brain state dependent brain stimulation, which uses the current monitored brain state to alter the stimuli to reach to a specific brain state. This is what we used here, closed loop brain state dependent brain stimulation. Much of the focus on BCIs has been unidirectional, meaning the loop is opened. Recently, few researchers have started to do scenarios where the feedback loop is closed. Thus far, the scope of brain-in-the-loop systems have been very narrowed, with systems designed for specific experiments. For example, the closed-loop music-based brain-computer interface for motion meditation in March 2019, and also a biomedical engineering team at Columbia University managed to use EEG-based neurofeedback to shift an individual's arousal so their task performance increases. Our goal is to introduce the idea of a generic client-server-based distributed brain-in-the-loop paradigm to study the vital issue of round-trip latency in such systems under various conditions. Let's take a look at our setup. At the front end of our system, the OpenPCI GUI calculates the power band of each electrode and sends it using lab streaming layer, TCP/IP based. At the back end, MATLAB receives and processes the transmitted power band and sends a corresponding feedback signal to the front end where the stimulus presented to the subject is altered. We have two hardware configurations. First, between the two laptops. The OpenPCI ganglion board is connected to 4 high-impedance differential electrodes connected to the scalp, alongside with 2 ground reference ear electrodes. The board communicates with the front-end HP laptop via ganglion dongle using Bluetooth technology. The HP laptop is connected to Belkin router through Ethernet cable. As for the back-end Dell laptop, the two laptops are Windows-based, communicating through a private network provided by Belkin router. The second configuration is the same, except here the HP laptop is connected to New Mexico State University public network, and the back-end device is a CentOS 8 Polywell server. The software system relies on 5 stack layers. OpenPCI GUI acts as the front-end application at the application layer, while MATLAB represents the back-end. Both applications request and send data to one another in addition to performing other processing tasks. Below is the transport layer, which creates the TCP or UDP header, and below it is the network layer where the source and destination IP addresses are added to generate a packet. This packet is then sent to the data link layer where the MAC address information is added to create a frame, which is finally sent to the physical layer to transmit the actual message bytes. OpenPCI GUI is a powerful open source tool for visualization, streaming, or recording biosignal data from an OpenPCI hardware device. It's a processing open source development environment which is based on Java. The GUI supports streaming data throughout different protocols: serial, UDP, Open Sound Control, and Lab Streaming layer. The serial protocol was disregarded as it's a wired connection, which restricts the system from having a cloud-based option in the future. Also, Open Sound Control was disregarded as it doesn't support a real-time communication. We choose Lab Streaming layer as it uses both UDP and TCP. As we know, TCP has error checking while UDP is faster than TCP, so Lab Streaming layer was the optimal choice since it can take advantage of both UDP and TCP protocol. One of the main problems was that the GUI doesn't support receiving streams. Not only that, but while the Lab Streaming layer is a full duplex communication protocol, no one had ever used it for receiving and sending simultaneously. So we added the receiving feature to the GUI. However, we faced another problem while creating the simultaneous communication. As the size of the frame received by the MATLAB changes, if no data is received, the MATLAB will not transmit any data back to the GUI. This causing the freezing of the GUI as it's stuck trying to pull in the expected MATLAB stream. So when this happens, the GUI doesn't send back anything, since the MATLAB is also waiting for the data. So the whole system got locked up and become paralyzed. To solve this problem, we forced the MATLAB to sense a dummy frame whenever it receives no data. The time difference between the GUI sending a message to the backend MATLAB and it receiving back a reply is a critical parameter for any feedback control system, as it affects the system stability. This time difference is referred to by loop delay or round-trip delay. To calculate it, the GUI client sends a flag of -1 for each of 5 sending frames. At the back end, the MATLAB server, if it receives a -1 flag frames, it sends a flagged frame to the GUI, where the GUI records the time it transmitted its flag and the time it received the reply from the MATLAB server. The GUI then stores these times in a text file along with the EEG band power and the frame rate information. A Python script extracts the flag transmission and reception times from the stored file and calculates the loop delay and other informations like the number of sending flags, the number of receiving flags, the sum of the statistics, and the time difference between 2 consecutive sending flags. Now let's take a look on the results and the effect of varying the MATLAB pose on the round-trip delay. Firstly, on the private network configuration between the two laptops. As we can see here, the box plot of loop delay in milliseconds for MATLAB poses of 20, 30, and 31 milliseconds. The loop delay is very high, ranging from 99 up to 6,717 milliseconds. The main common theme here for these 3 cases is the number of sent flags differs dramatically from the number of received flags. This difference decreases as the pose increases, reaching to a difference of 11 flags in the case of pose 31 milliseconds. The difference vanishes when the MATLAB pose is between 32 and 200 milliseconds. As expected, the median of the loop delay increases as the pose length increases. And as we can see here, this relationship is fairly linear. For MATLAB poses of 100 and 200 milliseconds, the median of the loop delay is almost equal to the pose lengths. From these 3 box plots, we found that for MATLAB poses of greater than 32 milliseconds, The increase in the median of the loop delay as the pause length increases is fairly linear. It's recommended in any statistical study to display results both with and without the outliers. In this table, we measured the mean, the standard deviation, the standard error, and the 95% confidence interval of the loop delay. In both cases, with the outliers and without the outliers, the round-trip delay are highly linear over the most of the ranges of the MATLAB pose. However, the results with the outliers removed generally have narrower confidence interval. Moving to the results of the second configuration, the HP laptop and the Bolywell server on a public network. MATLAB of pause 20 milliseconds doesn't provide sufficient time for even one of the 128 flags sent from the MATLAB to be received by the GUI. We also found out that the results aren't consistent. They change quite a bit each time we run the system, which is expected as the network congestion varies with the number of users on it. Even if we increase the MATLAB pause to 50 milliseconds, still doesn't provide enough time for the network to transmit all the sent flags to the GUI, causing the box plot of the loop delay to be very spread out and have large averages. The box plot of larger MATLAB delays, 100 and 200 milliseconds, show a consistent linear relationship between the loop delays and the MATLAB pause. This can be explained by the fact that a MATLAB pause of 100 or longer than that is long enough for the network to deliver the MATLAB flag acknowledging that it received the GUI sent flag before it then sends yet another flag. The table shows the network lag affecting all the results, leading to increasing the loop delay dramatically. The table also shows that the mean loop delay for 47 milliseconds MATLAB delay is 47.4 milliseconds after removing the outliers. Although it's not consistent, it shows that the system is linear whenever the network is reliable. The difference between the mean loop delay and the MATLAB pause for 100 milliseconds and 200 milliseconds are 0.4 milliseconds and 0.1 milliseconds for the HP server configuration, while for the Dell HP laptops configuration is 1.1 milliseconds at least. We believe this difference can be explained by the superior response time of the Bolywell server relative to that of the Dell laptop. This belief is borne out by observing the MATLAB-based back-end software executes in 0.3 milliseconds on the Bolywell server compared to 2.56 milliseconds on the Dell laptop. A very important question pops up, which is why the system needs at least a pause of 33 milliseconds to be stable and work properly. To answer this question, we used the ordinary sending script with no receiving for the GUI. We also used a Python script then to analyze this file to calculate the difference between the pairs of consecutive transmitted data blocks, which is the sending delay, as well as the usual statistics related to this difference. We found out that the GUI sends a frame every 33 milliseconds regardless the MATLAB pause. Taking a more detailed look at the statistics, we estimated the probability mass function of the sending delay. It's shown that the 33 milliseconds and 43 milliseconds represent the maximum probability of 0.22, while 32 milliseconds represents only a probability of 0.07. The significantly lower likelihood of 32 milliseconds explain why the 32 milliseconds MATLAB pause in the proposed closed loop system is a critical point where the loop delay is not always consistent. Also, the probability that the sending delay is greater than 34 milliseconds is very low. We managed to successfully place the participant's brain inside a feedback loop so that a stimulus can be altered based on the specific real-time brain response. It's a low-cost system as it relies on open-source products. The novelty of creating a general brain-in-the-loop system. We also found out that an obligatory 33 milliseconds MATLAB pause at the back end is essential. This pause is equivalent to the processing delay that a complex machine learning program might incur as it analyzes the incoming EEG streams and generates the optimal reply to the GUI. Thus, the potential utility of these results goes beyond the simplistic framework used here to calculate them.